So up to now we have seen various colligative properties. So whenever you come across about these solutions which are having the non-volatile solute, and up to now we have discussed the solute is a non-electrolyte. That means it would not undergo any ionization. Now let us see what happens if the solute undergoes ionization, called as dissociation, or some of the solutes may undergo association. So these leads to change the colligative properties. For example, if you see here RLVP, relative lowering of vapor pressure, we have seen this will be equal to mole fraction of the solute. So in the case of the dilute solutions, we have written this as the number of moles of the solute by number of moles of the solvent, or simply, which is nothing but weight of the solute by its molar mass into molar mass of the solvent by weight of the solvent. Yeah. So RLVP, relative lowering of vapor pressure, is inversely proportional to molar mass of the solute. Similarly, elevation of boiling point delta TB is also inversely proportional to molar mass of solute. And also depression in freezing point is inversely proportional to molar mass of solute. And osmotic pressure is also inversely proportional to molar mass of solute. That means whenever we come across about all these colligative properties, they are all inversely proportional to the molar mass of the corresponding solute. Suppose whenever we come across about dissociation or association, for example, if you take the sodium chloride NaCl, when NaCl is a electrolyte or strong electrolyte, when we place in water, this will ionize to give the corresponding cation and anions. Corresponding cations and anions, sodium ion and chloride ion. That means here the sodium chloride is able to give two particles. One is Na plus and Cl minus. At the same time, if I take the aluminum sulfate, Al2SO4 taken thrice. So this will give the corresponding cation as aluminum ion and the anion as the sulfate ion. So this is able to give totally 5 ions. So as we are aware that all the colligative properties are proportional to number of particles. That means in the first two examples, that means in these two examples, sodium chloride is able to give 2 particles. That means colligative properties will increase. At the same time, aluminum sulfate is able to give 5 particles. So every one aluminum sulfate is able to give 5 particles here. That means automatically the colligative properties also generally increases. And we are saying every colligative property is inversely proportional to the molar mass of solute. That means if number of particles increases, colligative properties also increases. And from this relation, colligative properties are inversely proportional to molecular weight of the solute. That means automatically the molecular weight of the solute must decrease, which is observed. So there is a deviation from the corresponding colligative properties whenever there occurs the association or dissociation of the particles. So that's why whenever we take electrolyte, If the electrolyte can be like, it can undergo association or dissociation. So whenever we come across about the electrolyte which is undergoing dissociation, in such a case, the colligative property will increases. So automatically the molar mass of the solute should decrease. At the same time, if you come across about acetic acid like molecules, it is observed that in benzene solvent, acetic acid undergoes dimerization. That means this 2 moles of the acetic acid CH3COOH in presence of the benzene as solvent, this will undergo dimerization. That means here the 2 particles have changed into a single molecule or single particle. That means in this case the number of particles decreases. That's why the colligative properties also should decrease. That means the molar mass which is observed should increase. That's why whenever we come across about solutes which are undergoing the association or dissociation, automatically the colligative properties will changes. So these leads to a conclusion that the molar mass which is observed, molar mass of the solute can be automatically will changes. That means it may increase or it may decrease depending on the dissociation or association. Now let us see in detail about what happens to the molar mass, that we call it as the abnormal molar mass. Abnormal molar mass. Just now I have told you here, whenever the solute undergoes dissociation or association, automatically the colligative properties will change or alter. So correspondingly the molar mass of the corresponding solute will change. That we call it as abnormal molar mass. So in order to understand this, the scientist called Vant Hoff introduced one Vant Hoff factor, which is I. So according to him, the Vant Hoff factor I is given by, it is the calculated molar mass divided by observed molar mass of the solute. So it's nothing but this is experimental value, this is calculated value originally, this is the observed value. The ratio of these two is given as the corresponding I. Nothing but the Vant Hoff factor. And we are aware that there is a relation which we have discussed already. The relation between molar mass and the colligative properties are inversely proportional. That's why we can write this as the observed colligative property divided by calculated colligative property. Observed calculated property divided by the calculated, which is the first one is nothing but the experimental value. Experimental value, the first one. So this is the actual calculated value by using a simple formula. So the ratios of these two is given by the Vant Hoff factor I. Of course, we can also write this another expression for this I as the number of moles of particles after dissociation or association divided by initial number of particles. Initial number of, here initial number of particles we mean to say the number of particles before dissociation or association. Before dissociation or association. So based on these corresponding values, suppose if you know the calculated molar mass and also observed molar mass, we can get the Vant Hoff factor. Or else if you know the observed colligative property and also calculated value of the colligative property, we can get the value of I, Vant Hoff factor. At the same time, if we know the number of moles of the particles or simply number of solute particles, moles after dissociation or association, and also the initial number of particles before dissociation or association. So from these we can calculate the Vant Hoff factor I. So once we know from this, we can come to a conclusion about what happens to the value of I. What happens to the value of I? The same value of I is generally introduced into the corresponding colligative properties. Once you got this, automatically we can get the abnormal molar mass. From that we can also calculate the corresponding colligative properties. So generally, if the denominator value is equal to the numerator value, then we can say I is equal to 1. The same we observed in the case of the electrolytes or substances or the solutes which cannot undergo any dissociation or association. For example, you take glucose, C6H12O6. In this case, this cannot undergo any association or dissociation. In such a case, I is equal to 1. The value of I is equal to 1. Similarly, in such a case, these two are also equal. That is, observed colligative property becomes equal to the calculated value of the colligative property. And also, the number of moles of particles before dissociation or association will be equal to initial number of particles. In such cases, the value of I is equal to 1, which is nothing but the Vant Hoff factor value is equal to 1. If it is a solute which undergoes either dissociation or association, let us see how to calculate the value of I. Now let us see about the dissociation. So let us take a solute. Assume general formula of the solute as AN, which is given by, or else it is given by n moles of the A. N moles of the A. That means if I take 1 mole of this solute, this is able to give the n moles. So assume initially, okay, we have 1 mole of this will be 0 moles. Okay, and after some time assume alpha moles of this is dissociated. Here alpha is called as degree of dissociation. Degree of dissociation. As these two are 1:n molar ratio, we should get compulsory alpha into n moles of the product should be formed. Initially we have 1 mole. In this 1 mole, alpha moles is dissociated. So remaining moles will be 1 minus alpha. And this will be n into alpha. N into alpha. So initial number of moles before dissociation is 1. And after dissociation, total moles. After dissociation, nothing but sum of these two. That is 1 minus alpha plus n alpha, which is nothing but 1 plus alpha into n minus 1. So here, before dissociation of this solute an, the value of number of moles we have taken it as 1, and after dissociation total number of moles is 1 into alpha into 1 plus alpha into n minus 1. So from this, as per the generalization, the value of I is nothing but the number of moles after dissociation is 1 plus alpha into n minus 1 divided by initial number of moles is 1. Nothing but number of moles before dissociation or initial number of moles. So from this we can have I minus 1 is equal to alpha into n minus 1, or alpha is equal to I minus 1 by n minus 1. Here alpha is called as degree of dissociation. Alpha is degree of dissociation. Degree of dissociation. I is the Vant Hoff factor, and here n is the number of moles or number of particles formed by the dissociation of a single particle. Number of particles formed by the dissociation of the one particle. For example, if I take sodium chloride, as I told you in earlier, NaCl will give 1 mole of NaCl and 1 mole of Cl minus. That means if we take 1 mole of NaCl, we should get 1 mole of Na plus ions and 1 mole of Cl minus ions. If I take a single particle of NaCl, this is able to produce 2 particles. In this case, the value of N is equal to 2. Or if I take the aluminum sulfate, Al2SO4 taken thrice, this is able to give 2 Al3 plus ions and 3 sulfate ions, totally 5. Therefore, the value of N is equal to 5 in this case. So simply, what is N means? N is the number of particles formed by the dissociation of a single particle. So from this you can take any solute which is undergoing a dissociation, and every case we can find out the value of I once we know the value of alpha as well as N, or else if you know the value of I, we can also calculate degree of dissociation. So alpha is given by I minus 1 by n minus 1. Of course, we can also write this as 1 minus I divided by 1 minus n. It's also true. From this we can get the value of alpha, which is degree of dissociation. Degree of dissociation. So whenever we come across about non-electrolyte, the value of n becomes here equal to 1. If the value of n becomes equal to 1, this becomes 0. That's why in such a case I becomes equal to 1. The case when we use the electrolyte is non-electrolyte, or the solute is non-electrolyte, that means it won't undergo any ionization. In such a case, the value of n becomes equal to 1. Therefore, I minus 1 becomes equal to 0, or simply I is equal to 1. That means there is no chance for the abnormal molar mass of the corresponding solutes. So conclusion here it is, whenever we use any non-electrolyte, in such a case there is no chance, or there is no particular abnormal molar mass. Abnormal molar mass.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.